Isaac Newton was all about describing motion. In addition to his 3 laws of motion, he was also able to describe the motion of the planets and the moon and what was able to keep them moving in their orbit. Along with that, he was thinking about why falling objects accelerate. His conclusion was that there must be some type of force being exerted on them. He did notice that no matter where you dropped an object, it always fell towards the Earth. He concluded that it must be the Earth itself that is exerting that force. If an apple would fall from a tree towards the Earth, and if this force acts at the top of the mountains as well, then maybe the force would extend to the moon itself. The problem Newton had was convincing people that there was some invisible force that did not need to be in contact with the object to act on it. So Newton set out to determine the magnitude of the gravitational force that the Earth exerts on the moon and the objects on its surface. And this is what he came up with: the law of universal gravitation. And it says that every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. So what does that mean? Well, we have 2 objects, mass 1 and mass 2. These masses are separated by some distance r. Newton said that the 2 masses have a force of attraction between them. This force depends on the mass, and the larger the mass, the larger the force of attraction. It doesn't matter which mass is larger, but bigger objects have a bigger attraction to other masses. So you have an attraction to the Earth, and the Earth has an attraction to you. You also have an attraction to a nearby tree that also has an attraction to you. When you lose your balance and fall out of the tree, you don't fly back up towards the tree, you fall back down to the Earth. The Earth is bigger, so it has more of an attraction. He also said the force of attraction depended on the distance between them. Actually, he said it was inversely proportional, so the further away mass 1 is from mass 2, the less the attraction. This makes sense as well. Jupiter is a lot bigger than the Earth, so it should have more gravitational attraction to you. But when you jump up in the air, you don't fly to Jupiter, you fall back down to the Earth because Earth is closer to you. The g is simply our universal gravitational constant. The value for this constant was determined experimentally nearly a century after Newton by Henry Cavendish. It has a value of 6.673 times 10 to the negative 11th newtons times meters squared over kilograms squared. Notice that this value is really, really small. To get an idea of how small it really is, take 2 objects that have a mass of 1,000 kilograms and are 100 meters apart. So these are fairly large objects, about a ton each, and they are pretty close, about a football field length. So those are pretty big objects relative to you, and they aren't very far apart. But when you solve for the force of attraction between them, you find that it really isn't much at all. So the force of gravitational attraction between those 2 objects is 6.673 times 10 to the negative 9th newtons. Now we want to focus in a bit on what direction the force is acting. In this picture, mass 1 is exerting a force on mass 2. So this is our force pair. If mass 1 is exerting a force on mass 2, then mass 2 must be exerting an equal magnitude force on mass 1. A lot of times we are dealing with really large objects like the moon and the Earth, so to make things simpler, we can just treat them as points in space. This point is located at the object's center of mass. We will talk more about center of mass later on, but for an object that is for the most part a sphere, the center of mass is right in the middle. So the gravitational force acting on the moon is acting on a point in the center of the moon. So the direction of the force always points along the axis that connects the center of mass of the 2 objects. As another example, what kind of gravitational attraction do you have for some person near you? Say you have a mass of 70 kilograms, and your classmate has a mass of 50 kilograms, and is sitting about a half a meter away from you. What is the force of gravity between you? Well, we're going to plug this in, and we're going to get 9.3 times 10 to the negative 5th newtons. So not much at all. We've been dealing with the acceleration due to gravity here on Earth for quite some time now, and we have always defined it as 9.8 meters per second squared. So where did that number actually come from? Well, initially Galileo measured it. He observed that any object dropped out of a tall building will accelerate at the same rate. Newton simply took that idea and described it in terms of some force acting on the object that caused it to fall in the first place. We can use our gravitation equation to determine this constant mathematically. We know from previous investigations that the force of gravity is also equal to an object's mass times some gravitational constant, which is what we're trying to find. We can plug this into our universal gravitation equation in order to solve for the value of the acceleration. The mass of the Earth is 5.98 times 10 to the 24th kilograms. The mass of the object doesn't matter because it shows up on both sides of our equation. The radius would be the distance from the center of the Earth to the center of the object. Now, pretty much anywhere you are standing on Earth will have a negligible additional distance from the center, so we can simply use the radius of the Earth as our distance between the objects. So if we get rid of that mass, really what we're left with is a gravitational constant for any given body is equal to the universal gravitational constant times the mass of the body divided by the radius squared. So for Earth, we get an acceleration of 9.8 meters per second squared. What's really cool about this equation is we can determine any body's gravitational acceleration using this constant. Say we want to land something on Mars. If we know the mass of Mars and the radius of Mars, we can use that to determine the gravity on Mars. We've kind of accepted that we can use the 9.8 meters per second squared as a constant anywhere we are on Earth. That's not entirely true. Earth is not a perfect sphere. There are mountains and valleys. The equator bulges a little bit. The Earth's rotation changes some things. So not everywhere on Earth has exactly 9.8 meters per second squared as the acceleration due to gravity. As an example, we can use the peak of Mount Everest to show how the gravity changes. We're going to use the same equation that we did before. The only difference is the radius will be 8,850 meters larger because the top of Mount Everest is that much farther away from the center of the Earth. Then we sub in those values. Notice adding nearly 9,000 meters did very little to affect our radius. And in fact, when we look at the value we get for g, it doesn't even really change it from 9.8. So at the highest point on Earth, the value that we use for g is negligibly different than that at sea level. So for our purposes, 9.8 meters per second squared is perfectly acceptable to use for the gravitational constant.